Okay, so now what we're going to do here is we're going to move on and do kind of our gain stage here. Well, the gain stage here, we work on the gain stage. Well, first off, before I start working on the gain stage, I should think about where I should take the output from. Remember, for a differential amplifier, the output comes off of the collectors. And remember, we have either a one-sided or a two-sided input. So we're going to use, not input, one-sided or two-sided output. We're going to use a one-sided output. So I'm just going to use this one here as my output there. And then I'm going to feed it in here. I'm going to erase this input 2 for a minute here. And I'm going to create, the temptation might be just to create a single transistor, like a common emitter configuration for the gain. But we can't just do quite that here. So if I look at this, what I'm doing here, and I'll explain what I'm doing here once I have it drawn. Okay. So what I now hear is I have a second biasing current here to bias this transistor here. And this is set in, this second one is set in, so here this would be my, here let me just, this is my gain stage. Now let's look at what we got here. We've got two transistors going here. We've got one that, if I think about this is kind of in a common collector form, right? Base and collector, base is where the input is, output is on the emitter, so common collector. And then this would be common emitter. Input's the base, output is the collector. Now, there's a couple reasons we do this. One is that this means that if we're talking about a common collector has a low output impedance, so we will get a good voltage gain then, because we don't have to worry about what the output impedance is here. If we were to connect it directly up to the base of the common emitter, we wouldn't have to worry about how much of the signal is getting through, because this is going to have a low output impedance on this stage. But another reason is a common collector gives us current gain as well. So that means we'll actually also be able to put out some current from this op-amp as well on the signal. So it won't just be that the voltage will be amplified on the signal, we'll also be able to have current going out on the signal as well. Now, this then is just our standard common emitter amplifier that we're looking at. And then we have another current source, I2. Now there's one final thing here, is we need my output stage. Now, the temptation is to say, okay, well, we're just going to put in a common temptation is to do something like this. and just take the output, bias this transistor somehow, gives us low output impedance. But there's going to be a problem with this. We're not going to be able to get a signal amplified completely. And it has to do with when you're both positive and negative. You're not going to be able to adjust fully between the rails. And so there's different types of amplifiers out there, like Class A, Class AB. But one of the things we're going to do here is we're going to do something that's called a push-pull. So we're going to take this output signal and tie it into two transistors. One's a PNP, and then one's an NPN. So we're doing a push-pull configuration. And then we take the output here. And so if you think about this as far as pins go, it turns out that this is my negative input, this is my positive input, and if you think about it, like on an 8-pin dip, this would be pin 2, this would be pin 3, this would be pin 6, and I believe that this would be what? Let me double check that here by going to the web here. This would be pin 4, and then this would be pin 7. That's a standard configuration for an op-amp. So this is my circuit here. This would give me an operational amplifier. Now, you can notice I've got one resistor here. Now, there would be 2 additional resistors for these current sources, or even more depending on what type of current source we're using. But let's look at this push-pull idea here. What's going on with this push-pull? Well, let's first imagine here that we have a signal coming in, a small signal coming in like this here. And we want to, because it's gone through its amplification and everything, and we want, the output to essentially be that, but we're essentially wanting the output impedance to drop. Well, let's look at the small signal model for that. So we've got 2 transistors there, and we've got their bases tied together. So I would have an RPN and an RPi-P. And then let's see, where are they tied together here? Well, those are between the base and the emitter. The emitters are actually tied together. And this is V out. This is Vn here. And then we would have, seems kind of silly, but we'd have isolated off to the side here. Actually, yeah, that's V out, V in, yep. And then isolated to the side here, we'd have, my current sources, which are between the emitter. So let's draw it like this. Between the emitter but you'd have 2 of them. they'd both be grounded then. And let's think about this for a second here. Because that would be the collector. So this would be GMN V pi. And then this would be in the other direction, GMP V pi. And so you can see why they call this a push-pull, is that if we imagine here V pi, which is actually the voltage across these two resistors here, we've got current coming in here like this. So we've got current coming into these, my small signal current. In one case, we get this current source essentially being on, and that would be kind of pushing the output up to the voltage that we need it to be at. And then in the other case, this one would essentially be on if it's like, because if we're in the positive half, let's just look at its positive half here. V pi is positive. These would be, I think, I'm trying to think of, do I have this? Yeah, I have this right. If it was positive, we're going to be pushing the voltage up. So we're going to be pushing, using this current going through these resistors, we're going to push the voltage up to whatever voltage we needed. And then if it's negative, we're going to be pulling it down. So, and I'll show you in a simulation what happens if you don't do a push-pull or something like a push-pull on the output. But that's it. That's our op-amp. Now the only thing, again, that we'd have to do is change these to actual transistor current sources. Now your simulation assignment is going to be to create essentially an NPN version of this. So you have to think about, I mean, in some sense you're just flipping the circuit 180 degrees, not 180, flipping it across the horizontal axis, because you're going to want these to be NPN devices. But you have to think about, well, does that mean, am I going to have to change these to PNP devices? So these might have to be PNPs. But, you know, can these stay? As NPN, or would I have to change those as well? Because remember, this is just coming off of the, that's just being tied into the output there. So I might not have to actually change these here, but if I think about this, and this having to be on the collector for an active load, if we try to move this up with NPN devices, either we might not have the transistors turned on, or we might not have them connected into the correct locations. So you're probably going to have to change those to PNP and think about how that would affect your circuit design. And then of course you're going to have to design for I1 and I2. And I will go ahead and just write in some values here for us. We're going to make I1 here 40 microamps and I2 200 microamps. Okay, so that's what you would design for, 240 and 200. So let's look at the simulations in the next videos.